Okay, midterm review section on color. Digging in, why? Why do we care about color? It sets the mood. It can leverage our intuition and our pre-attention. If something is green, we're going to see healthy, fresh grass, cool. If something is red, we're going to think threat, danger, heat, dryness. It can control chaos. It can reduce distraction if we limit color and use it to focus attention on specific things. Hello, number 4. And help create meaning. We can, employ the Gestalt principles and use color to create groups that might not otherwise exist, or use color as a common thread through an infographic where we're using a specific color to kind of pull your eye from element to element. All right, the differences between hue, which are the different colors, red, green, blue, yellow, orange, purple. Saturation, which is the intensity of the color, the purity of the color. Like in a photograph, you can think about desaturating something, which is just stripping the color out and reducing it to its grayscale version. And then value, how light or dark, how bright or dark a color is, or just the amount of white or black that's added. Shade is dark, and then tinting is adding white or lightening it up. And this is how we see it in ARC. It's kind of the custom color model window. You can adjust colors or choose colors by adjusting the value, shade, and saturation. So this is the hue. This is the saturation, full intensity down to desaturated. And then this is the brightness or the value. So taking any given color and then adding black to it, and that it's pulled out over here because these are the intensities, and then grayscale, and then over here, whatever you pick, you could add white to it, add to tint it, or add black to it to shade. Okay, there are different color models. RGB stands for red, green, blue. These are the 3 primary light colors. Like an LED screen will have a red, green, and blue light. And then the way you mix those 3 colors creates the other colors of the prism. RGB values, we won't get into the weeds too much, but HSV is hue, saturation, and value, and that's an alternative to RGB. I do think, like I said in my other video, I think it's a little bit more intuitive, but it doesn't really matter what you use here. And then the printing colors are cyan, magenta, yellow, and black, and that's what the K is. These are the subtractive colors, and it's just important to know in case you're ever going to print, hard print your graph or your plot, you're going to want to make sure you set up your colors in CMYK, because if you set them up on your computer screen, they're going to look great. Then you export this and send it to a printer, and your plot ends up looking nothing like you thought it was going to. So make sure you set it up on your screen using CMYK if you're going to print. Okay, so why is this important for charts and maps? Because it's all relative. Just like with the magnitude detection and how that those 2 circles looked so different in size because they were our perception of them was being influenced by the surrounding circles. The same goes here. This shade looks lighter because of the impact of the darker reds around it. The relative, our relative perception lightens this, whereas the surrounding colors here are lighter, so our relative perception of this is darker, but they're actually the same shade. And so this is why it's also low on the effectiveness rankings, because it would be very challenging to look at any one of these and be able to say that this color pink represents 17, this one represents 19. You'd go up here and go, oh, this looks more like 12. So that's the proximity. We're not going to be able to detect specific accurate values from these. Okay, data drives the color scheme. We talked in the first set of slides about nominal, ordinal, categorical, interval and ratio, all the different data types. It's important to know that when values are sequential, and this could be ordinal or quantitative, interval or ratio, we're just going from low to high. This is called a sequential color scheme, and it's going to be different than a diverging color scheme. Really be careful with diverging. These should be used when you have a mid-value that's meaningful, whether it's a world average or 0, and then you have positive and negative. It could be some kind of a proportional ratio, but this midpoint should have some kind of divergent meaning for your data set. I really strongly recommend you don't use diverging color schemes where you have a neutral value that peels away in one direction and then sort of an opposite color and building to a darker color from your neutral. Don't use these for sequential numeric values. And then of course there's the nominal, which are, I think of them as scrambled colors. They don't have any kind of order. They should be used to represent things that don't have any kind of order. And when you can, use them to leverage our intuition, using colors that make sense. All right, qualitative or categorical colors, the other thing to be aware of is to not, you have to pay attention to the luminance, and I maybe should have rearranged these a little bit. These colors are, these color ramps, there's 3 different schemes here. They're all fairly successful because each color is very noticeably different from the other colors in the set. And they're all about the same lightness and darkness. These some of them get a little funky. Like this is clearly much darker than this one, like higher contrast against the background. That is going to cause some problems, because contrast obviously draws our eye. These I think are much more consistent. I think these run into a little bit of trouble. The ggplot2 hue set is much more consistent. Every color is very different. Easy to distinguish, and they're all very even in contrast against the white background. When we look at these through kind of a color blindness or a color deficiency filter, you run into a different set of problems. So that ggplot2 hue that I really liked, if I had a color deficiency in my cones, I would completely lose the differentiation between 4 of those colors, and actually these 2 are really close as well. These 2 are very similar. They're actually all pretty terrible, but that Okabe Ito fares pretty well. So even though we have some issues with contrast here and a lot of difference in luminance, this one actually kind of passes the color deficiency test. For sequential, again, light to dark, you can go from one color to a next. Doesn't just have to be shades of one specific color. You can have multi-hue. So more than monochromatic. This is monochromatic. This is multi-chromatic, I guess. Yeah, but again, you need to be thinking about luminosity. If you were to pull the color out of these, how would they translate? And I'll show you some examples of that. But these are really good for quantitative values, and this is another example of multi-hue. And I think the key is that you have enough classes here that the classes step and make sense, going from one to another. If you were to break this is 7 classes. If you were to reduce this color scheme down to 3 classes, you might be left with yellow, kind of bluish green, and purple. And between the 3 of those, I think it'd be really hard to see a graduation, a natural graduation between them. For divergent color ramps, again, neutral colors in between and then diverging in 2 different directions. It's kind of like 2 sequential scales stitched together at that neutral point. So just be careful not to impart bias. Like I said before in the original set, be aware of these intuitive meanings of the color, and be aware that the luminance changes. These should change in color, but also as they should be building in intensity as you move away from the neutral midpoint. And then we can't talk about color without talking about the importance of the lack of color. My recommendation and a good practice is to start your plots in black and white. Desaturate everything and get rid of all color, and then add it in carefully and deliberately where it's necessary. Most software packages plot everything up in color automatically. Excel does it, Tableau does it, R does it. It's just the norm. But I would say strip it out and then add it back in when you have your plot really dialed in. I love the way this is labeled with the labels inside the numbers. I think that's so cool. This is kind of like showing data over time. And here they're using color to draw our attention just to 2 countries. Another example of that is to desaturate. Here we have 4 different regions, and all the color is just a lot. And when we desaturate, you don't have to get rid of color, but just turn it down a little bit. It lets us, focus on specific features and start to tell a story. Okay, and then last but not least, the mighty rainbow color scheme. Hopefully you just went through this last week, and so this is a real refresher, but I'm going to talk quickly through some of the fundamental problems with the rainbow color scheme. So the order between colors isn't intuitive in that we can see a graduation between them, but we know they're connected, but only if there are enough classes to maintain the connection. So as we start reducing the number of classes, kind of like I just talked about with the other one, that starts breaking down a little bit. So here we have so many classes, an N of 48, that it would be impossible to distinguish between some of these different colors. Like if we created a choropleth map or had a scatter plot and we were using 24 different colors of the rainbow, how would you ever be able to tell the difference between all these greens? You never could. Here we've got a pretty clear set, so an N of 6 works pretty well, but when we get down to 3 different classes, now there's no order whatsoever. And even here, the order between red, yellow, and green is not at all clear. Here I might be able to buy it, but we really have lost that sense of graduation. Okay, the other issue is luminance. So we have different hues, but these hues are different shades, different lightnesses and darknesses. And as we kind of scroll through the rainbow color scheme, the luminance or the brightness goes up and down. So if we strip out the color here, we start with white, and then we darken, and then we lighten again, have a bunch that are the same, and then we darken again. And then we would basically wrap back around to white. So it's always a good idea to test for luminance by turning the color off in your plot and check it out, and just make sure that you aren't imparting some kind of bias. Okay, so yeah, there's a lack of perceptual ordering. We don't really know where the rainbow color ramp starts. Does it start with yellow? Does it start with red? It's impossible for us to know which number is the highest. Okay, the luminance thing, again, people see darker colors as deeper or lower and lighter colors as coming out toward them. And that's why with topography, it's really important, like with hillshade, that you make the high values in elevation when you're coupling it with hillshade. Make sure the high values, mountaintops, are being drawn with lighter colors and lower elevations are being drawn with darker colors. That's intuitive for humans. When you flip that, you sort of work against yourself. And so, like I was saying on the last one, the luminance really breaks up the natural sequence of the rainbow scale. We get kind of roller coaster fluctuations in here. That just kind of creates confusion. Okay. The third or fourth, I'm not even sure what we're on now, but another major problem with the rainbow color scheme is the uneven representation. So if you look back and forth here, you'll see that some colors you pass by really quickly, and then some go on forever, never, 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 and then quick, and then longer. This is another long one here. So we don't have a one-to-one representation. If we were to cut this into bins and we're using it to map some kind of interval or ratio set of values, we don't have a one-to-one representation with the values along some kind of consistent scale. That's definitely a problem. So we don't have the same proportion of green as we do of yellow. Problem. Perceptually graded color schemes. I don't think I want to talk about that as much as I want to talk about this. So these rainbow color schemes, or any of these color ramps, are sort of computer generated, and you can see that they're very inconsistent. You know, this is pulling just that little section of the green that went on and on and on, and then the light blue that kind of flashes by, going to dark blue. Okay, so yeah, right. So the way this might be, in RGB, there might be a consistent stepping between each one of these colors, but the way we perceive them is not even. Okay, these rectangles do have an even distribution in hue, and the colors are evenly distributed. This is called a perceptually uniform color scheme. The luminance is also preserved. Here we have a peak in luminance right here in the middle, and then it kind of goes to dark at both ends. But here the luminance is very consistent all the way across. So again, this is called a perceptually, do you remember? A perceptually uniform color scheme. Okay, and my final, I don't know what you want to call it, caveat about colors is don't use them thoughtlessly. Don't accept the defaults and then just run with them. Don't take color just because it's given to you. Get rid of it and add it back in because you choose to. And then don't use color just for the fun of it. Make sure that you're being thoughtful and deliberate, consistent. I mean, here we've got classes that are being colored 2 different ways. I mean, this is just a disaster here. Okay, and then if you have this many colors going on somewhere, if you need more than a handful of colors, there's probably a better way to do it. And I think this is a really good example. Here we've just got all these different things that we're mapping, you know, maybe over time, before and after, who knows. But we're basically trying to compare the differences between these two. And so here they flipped it and took the whatever, A, B, C, D, E, F, G, and then just mapped the values this way instead, against each other. No need for color at all. A much simpler way to show the information. And then this is an example of putting a couple of these things together and why the rainbow color ramp is a pretty bad idea. First of all, it's just kind of a lot of color, and you don't want to make things so garish, I think. Yeah. So anyway, this is the rainbow color ramp applied to a county level map of Texas, encoding the percentages of the population that identify as white with different colors along the rainbow color scheme. So if you look at this, where are the areas, the obvious areas of high percentages of the population identifying white, and where are the low ones? I mean, hopefully you can see that there's absolutely no way to determine without a legend what is high and what is low on the rainbow color scheme. Where does it start? You know, where's red? Where does that fall? Is it in the middle? Is it at the end? You shouldn't need a legend. You should be able to use color intuitively and create a one-way kind of uniform color scale. So here is the color scale that came with it. You know, red and almost red are both ends. This is a terrible idea. Okay, here I've desaturated it. Notice the luminance. Notice that the high and low values in the rainbow were both kind of reddish. Here they're both dark. So we go from dark to light, a little bit of dark, back to light, and then, well, to really dark, back to almost dark. I mean, it's, again, a terrible idea. So we've just kind of lost all intuition and are leveraging nothing here, and basically just blasting our audience with a lot of color. Okay, and last but not least, just one more note on color deficiencies. With the divergent color schemes, just be aware, red and green are the most common kind of color deficiencies that are difficult for people to see, people with color deficiencies. So really try and avoid red and green, and especially on a divergent color ramp, because it's so hard to distinguish red and green. These are the three different color deficiencies, red, green, and blue. And you can see that the blue color deficiency is not as common. It's actually pretty rare. It's preserved here. We can see the difference between the two ends of the divergent ramp. But with both the red and the green color deficiencies, we've really lost that message here. And then with a blue to green divergent color ramp, the most rare blue color blindness or color deficiency is where we lose it, but we preserve it for the red and green, which is more common. So, again, take your data into some of these, online, but they make apps for your phone where you can use the camera and you can run your plots through a color deficiency filter and just test for readability. And it's also a really good idea to test against luminance in case your plots get reproduced in black and white. Like, let's just say the newspaper picks up this awesome research that you've been doing and they print it in grayscale and your story gets completely screwed up. So, just test a couple different ways.